Okay, so let us continue our study of propositional logic. So, to do a very quick recap, we first looked at the syntax, and in the syntax once you define an alphabet, you get a language. Yeah, so, the alphabet includes, if you remember, things like connectives and propositional variables and so on essentially. So, a language is basically a set of sentences. And the alphabet is essentially things like and, or, not, p, q, r. Without going into details, these are the kind of things that we had actually. And then we have semantics. So, as far as propositional logic is concerned, by semantics we mean truth functional semantics. We defined the notion of truth values. And we saw that there are three kinds of formulas or three kinds of sentences in any language. One is tautologies, these are sentences which are always true, and when we say always true, we basically mean they are true for any valuation of the atomic propositions. So, whatever the atomic propositions are p, q, r, s, t and so on, whatever valuation you give to them, which means true or false, these sentences will always be true, and a trivial example of that was p or p or not p. Then we have sentences which are contradictions, and these are sentences which are always false, which means that any valuation that you choose, they will be false. And an example of a contradiction is this sentence, which is a negation of the tautology that we have seen essentially. I have particularly chosen this example because there is this relation between contradictions and tautologies, that if you have a tautology and you put a negation sign before that, it will become a contradiction and vice versa. So, in this case we have taken a tautology p or not p, put a negation sign in front of that, and it has become a contradiction. And the third kind of sentences are contingencies, and by contingency we mean that the truth value of the sentence depends upon the valuation that you are choosing. So, a sentence like p implies q, for example, will be true if, for example, you choose p is equal to true and q is equal to true, but it would be false if you choose p is equal to true and q is equal to false essentially. So, its truth value is not independent of the valuation, it depends upon the valuation essentially. So, we would be more interested in tautologies and contradictions, because we are interested in proof systems. We want to show that whenever certain formulas are always true, we have a way of reaching to those formulas. So, before we do that, so when you talk about contingencies, we essentially talk of satisfiability. And the well known SAT problem, which is common in many areas of computer science, is an instant is basically addressing the satisfiability problem. So, you are given some sentence, you are asking the question, is there some valuation which will make this formula true or which will make this sentence true. So, that is a different kind of a game altogether, we will not get into that. We are more interested in tautologies and contradictions essentially, and we will see what we talk about. Then we define the notion of entailment. So, if you remember the notation, we said that a knowledge base K B, which is basically a set of sentences that are you are given entails a sentence alpha whenever alpha is necessarily true as long as the KB is true essentially. So, whenever KB is true alpha will be true, and this is the notion of entailment essentially. Correspondingly, at the syntactic level we have this notion of provability or the notion of proof, and that is the concept that we are going to be exploring in most of this course essentially. And we write that a knowledge base proves, or you can prove a sentence alpha given a knowledge base essentially. And essentially we are interested in that kind of a logical machinery where provability implies truth or entailment and entailment implies provability, which means we want to be able to prove all true formulas and we want to be able to prove only true formulas. Once we have such a machinery, we can actually throw away the notion of semantics and we can just work with the syntactical machinery, which is the proof machinery essentially. Now, a proof, for a proof system to work, we need a language that the syntax gives us, plus we have rules of inference. So, let us look at proof systems. So, let me start with an example rule, the rule that we have been, we always start with more or less whenever we look at logic, and that is the rule of Modus Ponens, which we have seen earlier. And the rule is written most commonly as P, and P implies Q, then Q. So, the sentences above the line are the given or the antecedents, and the sentence below the line is the consequent or what you derive essentially. We also write this, if you remember, as P comma P imply Q, and we use this notion that the symbol that we have is Q essentially. And this rule we will call as MP, which is a short form for Modus Ponens essentially. Now, the first thing to emphasize, which I have done earlier also, but just to repeat, that P and Q are propositional variables. Which means you can plug in any sentence in place of P or Q. So, for instance, so what this defines is only the form of the argument. So, I could have written something like this, A and B or C, and then I can write A and B or C implies R or S, and from this I can imply R or S. So, if I do this, I am still using the rule of Modus Ponens, because essentially what I have is something, a sentence of any kind, which in the original notation we said P, but in this particular example that the sentence is A and B or C, and then we have another sentence which says that A and B or C implies R or S, and from there if we can add R or S, then we can, this is also an instance of Modus Ponens. So, this is just to emphasize the fact that when we say P and P implies Q, these are propositional variables and you can plug in any sentence. It does not even have to be in propositional logic, it can be in first order logic or any modal logic or any other logics that one may explore essentially. So, what really we should write is something like this, that if you have sentence 1, whatever the sentence is, in fact in any language, and if you have another sentence which is of the form sentence 1 implies sentence 2, then we can infer sentence 2. So, this is a rule of modus ponens, and we saw that there are other kind of rules. So, what do we mean by rule of modus ponens? That it is a form of argument that we are willing to accept, which says that whenever we have two sentences which match this pattern, that one of the sentences of the kind P and the second sentence of the kind P implies Q, then we can make an inference of the third sentence which is Q essentially. Whenever this form is conformed to, the argument will be accepted as valid. And if you remember, we had said that MP is valid if, or rather I should say because this sentence P and P implies Q is a tautology actually. So, every valid rule of inference is based on a tautological implication. We had seen that in the last class. This is just a quick review of what we did essentially. So, what is a proof system? A proof system essentially does the following, that it is an algorithm you might say, that pick some rule, and when you say rule we mean a rule of inference with matching antecedents, which means in our knowledge base there are certain formulas which match the antecedents, then add the consequent to the knowledge base and put this whole thing into a loop essentially, okay, until some termination criteria. We will look at this. This is by and large the outline of any proof system essentially. A proof system essentially is a sequence of applications of rules till certain criteria is satisfied, and we will look at what this criteria is essentially. Another important point to note is that this question of sum is really a key question essentially, because once you pick the right rule you will get a short proof. If you pick wrong rules, then you may produce formulas which are not of any use to you essentially. So, that sum is going to be a very critical thing essentially. So, let us talk about the termination criteria. If I can get a new page. So, by and large we tend to distinguish between two kinds of proofs. One is called direct proof, or we use a term often natural deduction. So, we have thrown in the term deduction here. So, at this moment we will simply say that deduction is that form of inferences which use valid rules of inference essentially. And what we do in direct proof is the termination criteria is until alpha is added to the KB, where alpha is the sentence that you are looking for. You want to prove a certain statement, and we use the term theorem. In a direct proof you keep adding formulas till you get the formula that you are looking for, and that is the most natural form of proof. and that is why we always often call it natural deduction essentially. This name is also attributed to a logician called Gentzen, and in fact there is a whole way of proving things which is known as Gentzen systems essentially, which are basically natural deduction systems. And in Gentzen systems we essentially have a proof tree where the leaves are what is given to you. So, P 1 and P 2, if they are sentences, they may give you P 3 and then P 4 and P 5 may give you P 6 and this may give you P 7 and some formula P 8 and this will give you alpha. Alpha is the formula that you are interested in. So, Gentzen systems are natural deduction systems where the leaves are what are given to you and the internal nodes are the consequence that you have added, and you terminate when you add the consequent that you are interested in essentially, which is alpha essentially. The other form of proof is called indirect proof. And in indirect proof, most of the time we will look at two systems of indirect proof. One is the tableau system and one is the resolution method. In both these methods, you try to is kind of proof by contradiction. And what do we mean by this? That if you add negation of goal. So, we often use the term goal as for the formula that we want or the sentence we want to prove, which means negation of alpha to the knowledge base, then this results in a contradiction, which we write as so, remember that this symbol that I have written on the right hand side is the symbol for bottom. It is a sentence which is always false, and essentially what you are saying doing in a proof by contradiction is that if you add the negation of the goal, then you end up with a contradiction, which means the negation of the goal must be false, which means that the goal itself must be true essentially. So, we will look at this in a little bit more detail. Let us focus on the direct proof to start with, and keep in mind that our goal is to be able to write programs which will do all this work for us essentially. So, this whole exercise is called theorem proving, and we want to write programs which are often called theorem provers, and what they will do for us is that we will give them a set of things which are given or true, and we will say show that this thing can be derived, and the theorem prover would produce a proof of that essentially. That is our interest essentially. So, we would prefer those methods where it is easy to write an algorithm for doing that essentially, and we will see as we go along that indirect proofs are easier to implement than direct proofs, because very often direct proofs involve certain amount of guesswork essentially, or certain amount of creativity if you want to say, in choosing the rules and things like that. So, let us look at an example of a proof. So, let us say some sentences are given to you. So, which we use the term given. So, if you remember your school geometry, school algebra, you said this is given and to show essentially that kind of a thing, or we can use a more formal term which is the premises, which you accept because of some reason. It could be because of the domain that you are talking about, the sentences pertain to certain domains. So, you will say that P is true for example, or P and Q is true or something like that. So, let us say we are given some sentences. So, I am just choosing some random sentences here. So, let us say P and Q implies R, that is given to you essentially. You do not question why it is true, it is something which is given to you, and let us say not q or S implies T. You can plug in any sentence for P or Q or R. So, for example, you could say P stands for Alice likes mathematics, Q could stand for Alice likes physics, then R could be Alice will study science or something like that. So, if Alice like maths and Alice likes physics, then Alice will study science or something like that. Essentially, you can plug in virtually any sentence. We are not really interested in what you are talking about. We are not interested in the content of the thought. We are interested in the form of reasoning essentially. Let me just take a very simple example which says that not T and P. Let us say just these things are given to us. I hope this works, and we want to show. So, let me write it here, alpha is equal to R. So, we are saying that if the first three sentences are given to us, does R follow logically from this? So, as we have seen earlier, one way of doing this is to construct a truth table, just construct a large formula based on this and see whether R turns out to be true or not, but we are interested in proof methods right now essentially. So, let us do a proof of this. So, what I am writing in blue, if you can make out, are sentences that come out of this. So, for example, not T. So, this comes. So, typically the way we write proofs are that how did you get this not T? We got it from sentence 3 and a rule called simplification. You have to give a justification for every sentence. So, you can only use valid rules of inference essentially 5 P. Okay, again similar 3 and simplification 6 negation of not Q or S. How do I get this? I get this from 4 and 2 and a rule called Modus tollens. It is one of the rules that. So, basically a proof system will have a set of rules of inferences, and a lot of time was spent by logicians in trying to figure out what rules of inference do we need for a system to be complete essentially. So, if you have more rules of inference, you can get possibly shorter proofs, but then the number of choices become larger at the same time. So, there is a trade off between having more rules or less rules anyway. So, then we get this. So, we push this inside, we get Q and not S, which is from 6 and De Morgan's, which I had not spoken about, but any textbook on logic will tell you that when you push the not inside, I have skipped a step in which I said that not Q should be Q essentially. From this I can get Q, which is 7 and simplification. Then I can get P and Q. So, I get it because I have P which is given in sentence 5 and I have Q which is given in sentence 8 and there is a rule called addition. And finally, I get R because I have 9 and 1 and our favorite rule which is modus ponens essentially. So, I have managed to add some formulas to the knowledge base. So, not T, then P, then other formulas, and in the end I ended up adding a formula which is the formula that we were interested in, which is R essentially. So, you can also write this in a form of a tree, as I said, a natural deduction tree. So, for example, at some point you would say that from this sentence and from this sentence I get R. And the other things, you can actually construct a tree from those 3 sentences you can which ends up with R as a root node essentially. So, this is a basic idea of a direct proof essentially. Now, in this we assumed that something was given to us and then from there we moved forward to this thing. So, one requirement of direct proofs is needs a set of starting sentences, because if you remember the application of the rule says that pick some rule with some matching data. Where is the matching data? It must be there in your knowledge base essentially. So, you must have some knowledge base to start with, to which you can apply these rules. Now, there are 2 kinds of so these starting sentences, they are called axioms. By axioms we mean that something that we accept as true, and there are 2 kinds of axioms. One is logical, which basically means that they are tautologies, and the other kinds are domain specific, which are given to us by the domains. So, these domain specific axioms are the ones that we started off with here essentially. We accepted these facts to be true because somebody said that this is true, and in any case we are interested in the entailment question. So, what is the entailment question we are interested in is that this set of sentences, which is, let me write here, P and Q implies R comma not Q, or S implies T comma not T and P entails R. This is the question that we were interested in. Of course, this is not entailment, this is a derivation, but we are interested in those machines where the derivations will always correspond to entails. We have said that we are interested in machines which are both sound and complete essentially. So, if my machinery produces R as it is done here, then R better be true, otherwise what is the use of having such a machine. So, we need a machine which is sound essentially. Okay, so, in the next class we will look at some of the early logical systems where the axioms were tautologies essentially, and then we will show that even working with domains with problems like this can be reduced to looking for tautologies. So, that is why at the beginning of the class I said that we are interested in tautologies essentially. If you can find all tautologies, we can find problems like this as well essentially. Okay. So, we will do that in the next class essentially.